take a look at it. So we'll do nitrous oxide as orange this time. So 1/3 of the molecules in here, or 1/3 of the moles, is nitrous oxide. 2/3 of the molecules or moles will be water. We'll do water in black. So I put too many oranges there. So let's first visualize this as the Dalton's mixture. What did you come up with? How much nitrous oxide do we have? How much nitrous oxide do we have? This is a Dalton's mixture. How many liters of nitrous oxide do we have? Well, maybe this takes more time to sink in, so I'm just going to tell you, and then you go home and then you sort through it, try to figure it out. Yeah. This often happens in science. You go to scientific conferences and you don't really understand it fully until you go home and figure it out. Or you start reading some background literature on it. So a lot of conferences like that. How many liters do I have? I'll tell you. I have 82.3 liters of nitrous oxide. So I have 82.3 liters of nitrous oxide. Okay, how many liters of water vapor do I have? Nitrous oxide is supposed to be orange. How many liters of water vapor do I have? I have 82.3 liters of water vapor. It's two of gas. It says more. This is twice the number of molecules. It's kind of high pressure. Well, it's not that high pressure, but it's supposed to be twice the number of molecules. It's 2/3, 1/3. Yeah, 2/3 of the molecules are water, 1/3 is nitrous oxide, because we form 3 moles of gas altogether. 1 N2O and 2 H2O. Okay, what are the pressures? What's the pressure of nitrous oxide that I have?
1/3 of the pressure.
1/3 of the pressure. 1/3 of the pressure, that's, what is 1/3 of 896? It's the same fraction, so it's going to be 1/3, 896, 1/3, 896, 4 comes out to, because the mole fraction is the same as the pressure fraction, so the mole fraction is 1/3, the pressure fraction is going to be 1/3, so 1/3 of 896, so 896 divided by 3. 298.6. And so this is going to be 298.6 torr. So I'll have 82.3 liters of nitrous oxide at a pressure of 298.6 torr. And then the other third of the pressure will be water vapor. Or not 1/3, the other 2/3 will be water vapor. Twice as much pressure. 597.3. 597.3 torr. Okay, this is important because when we do stoichiometry, we need this. We need the moles of gas. So let's say I want the moles of N2O. The moles of N2O will equal, okay, PV equals nRT, so it'll equal PV over RT. And so it's important that we put in the correct pressure and the correct volume. The correct pressure would be 298.6. We have to convert it into atmospheres, of course. And the correct volume is 82.3. goes in here. But what often happens with gases is people get it mixed up. They get Daltons and Avogadros mixed up. And what they end up doing is they end up putting the wrong pressure volume combination in the ideal gas law. This is a common error. So the moles of water will equal PV over RT. Well, the pressure in this case is going to be 597.3, the volume is 82.3. Temperature is fixed. I wasn't going to bring up Avogadros, but the problem is that sometimes people will see it, and the book talked about Avogadro's law, so sometimes people get it mixed up. And so, at the risk of mixing it up even more, I'm going to talk about it. I'd rather ignore it completely, probably it'd be the easiest thing to do, but sometimes people hear about it. So let's look at the same exact mixture using Avogadros. If I visualize this mixture as Avogadros, how much nitrous oxide, how many liters of nitrous oxide do I have? How many liters of nitrous oxide do I have? No, it's not. If I visualize this using Avogadros, then the mole fraction is the same as the volume fraction. If I visualize this using Daltons, the mole fraction is the same as the pressure fraction. And so it turns out that nitrous oxide is 1/3 of the mixture. Therefore, 1/3 of the volume will be nitrous oxide. 2/3 of the volume will be water vapor. And so what is 1/3 of the volume? It's going to just be 1/3, 82.3 liters. So this is going to be my nitrous oxide. Which is this orange. This orange is not very visible though. Put it in there. So what is 1/3 of 82.3? So 82.3 divided by 3. 24.43. 24.43 liters of this will be nitrous oxide. And then 2/3 of this will be water vapor. So what that means is this. Well, what's the pressure? If I have 24.43 liters of nitrous oxide, what is the pressure of this? What ATM? Not what ATM. 896 torr. That's right, 896 torr. And so I'm going to have 896 torr of nitrous oxide. The volume is going to be 24.43 liters nitrous oxide. What's the pressure of water vapor? 896. And so I have a choice. I can keep the volumes the same, or I can keep the pressures the same. They're going to give me different number combinations. I have to make sure that I don't do this. I have to make sure that I don't do a pressure and a volume fraction at the same time. That is, I got to make sure that I don't cut the volume by 1/3 and the pressure by 1/3 simultaneously. You know, if I keep the volume the same, the pressure gets cut by 1/3. If I keep the pressure the same, the volume gets cut, it has to be cut by 1/3. And so here we calculate the number of moles of nitrous oxide is equal to PV over RT. But this PV combination is different. This pressure now is going to be 896 torr. This volume is going to be 24.43 liters. But take a look at these two. These two will give me exactly the same answer. You see? I'm going to get the same number of moles, either calculation. So I have a choice. I could either visualize this mixture as a Dalton's, or I could visualize it as an Avogadro's, and then do the calculation. I can't do both though, because both don't work simultaneously. It's either or. It's either Dalton's or Avogadro's. So let's go on here. So they told us the total volume of gas produced. And they want to know how many grams of ammonium nitrate exploded. And so we have a choice in this particular we take our solid ammonium nitrate, and this is going to form nitrous oxide and 2 waters. I have a choice. I could go liters of nitrous oxide to moles of nitrous oxide, moles of nitrous oxide to moles of ammonium nitrate, moles of ammonium nitrate to grams. Or I could go liters of H2O gas to moles of H2O gas, moles of H2O gas to moles of ammonium nitrate, moles of ammonium nitrate to grams. Both of these will give me the same answer because they formed in a stoichiometric. There wasn't a limiting reagent or excess reagent. Both of these formed from the exact same reaction in a 1 to 3 and a 2 to 3 ratio. And so let's just do the nitrous oxide because it's 1 to 1, or the water. Which one do you want to do? Nitrous oxide or water?
Nitrous oxide.
We'll do nitrous oxide. And so what we have is we have the volume. Okay, which one do you want to visualize it? Do you want to visualize nitrous oxide as a Dalton's, or do you want to visualize nitrous oxide as an Avogadro's? Dalton's. Okay, if we do Dalton's, then this is it. But the way we're going to figure out the moles of nitrous oxide is we're going to use ideal gas law. So in this case, it doesn't lend itself as easily to using the molar volume. So I'm just going to go for moles of nitrous oxide, although we could do a molar volume too. If we did a molar volume would have worked if we visualize this as a Avogadro's. If we visualize this as an Avogadro's, then 82.3 liters out of that, 1/3 is nitrous oxide. And then we could use molar volume straight. But since we're using Dalton's, we have to use the ideal gas law. Even if we did Avogadro's, we could still use the ideal gas law, but Avogadro's gives us the choice of using molar volume because molar volume is based on Avogadro's. In fact, let me just show you something before I forget. You saw this before. But it might not have seemed like it. This is Avogadro's law. This is not Dalton's. The only way this works is what's the pressure of O2? The only reason this works is what's the pressure of O2? Well, 1 atmosphere. What's the pressure of H2? 1 atmosphere. What's the pressure of H2O gas? 1 atmosphere. The only reason this works is everything is 1 atmosphere, 1 atmosphere, 1 atmosphere. This is called Avogadro's law, the law of combining volumes. Everything has to be at 1 atmosphere. So I got 1 atmosphere of O2, I got 1 atmosphere of H2, I got 1 atmosphere of H2O. So if this were in a mixture, then 50 plus 100 gives me 150 milliliters of reactant. So I have 150 milliliters of reactants, 100 milliliters of product. Avogadro's bomb. This is why people get mixed up, because people get mixed up as they look at this and they think Dalton's law applies here. No, Dalton's law does not apply here, because if you take 1 atmosphere plus 1 atmosphere, what do you get? You don't get 2 atmospheres. You take 1 atmosphere and 1 atmosphere, you get 1 atmosphere. So the volumes have to add. Volumes are additive because this is the law of combining volumes. Volumes are additive. And so this, the reason I'm going through this is because people get it mixed up all the time, and then they mess up the calculation because they use the wrong pressure volume combo here. So we've got to make sure we're using the right pressure volume combo, which is this one. And so N is equal to PV over RT. Now the pressure, we said, is going to be 298.6 torr. So 298.6 torr. And then we're going to convert that to atmospheres. Yeah, 1 atmosphere is 760 torr by definition. And then the volume is going to be 82.3 liters. 82.3 liters. The law of combining volumes fails here. The law of combining volumes doesn't work. Because if I take 1 liter plus 1 liter, I don't get 2 liters. The law of combining volumes fails. In other words, Avogadro's fails because Avogadro's only works when we have constant pressure, or like that. But we don't have constant pressure here. This is more Chem 1A-ish because it's not so easy. R, 0.08206 liters times atmosphere per mole times Kelvin. T is the temperature. Write it down. 447 degrees C. So I'm just going to calculate that. 447 C plus 273 plus 720 Kelvin. So let's see, torr cancels, atmosphere cancels, liters cancel, kelvins cancel. And that gives me 1 over moles. So if we invert multiply, we get moles. So I'm going to go ahead and calculate this out now. 298.6 divided by 760 times 82.3 divided by 0.08206 divided by 720.547. So we went from the volume, liters, and pressure and temperature to moles. And so once we get moles of nitrous oxide, then we're going to go over here to get moles of ammonium nitrate. And then from moles of ammonium nitrate, we'll go to grams of ammonium nitrate. And so it's a 1-to-1 mole ratio. So we'll just do it using dimensional analysis here. I have my 0.5472 moles of nitrous oxide, 1 mole of ammonium nitrate per 1 mole of nitrous oxide. Okay, then I need the molar mass. The molar mass, I have 2 nitrogens. Each one's 1401, so 2 of them will be 2802. I have 4 hydrogens, will be 404. I have 3 oxygens. 3 times 16 is 3248. So that gives me 6, 0, 12, 80.06 grams of ammonium nitrate per mole. So that should give me the grams of ammonium nitrate here. 0.81 grams of ammonium nitrate were required to generate that much nitrogen gas, or nitrous oxide gas. For every one of those that forms nitrous oxide, 2 of the water is formed. Okay, so we did 37 to 39. Were there any other questions? No. Okay, we're going to go to chapter 15. Gases, liquids, solids. Let's take a look at some. Before I do that, let's take a look at some visualizations of what's happening with gases, liquids, and solids. At the molecular level.
States of matter are gas, liquid, and solid. Gases assume the shape and volume of their container. Particles of gas are separated from each other, move in straight lines, and in a completely random manner. They change direction only when they collide with each other or the container. Liquids have a definite volume and assume the shape of their containers. The particles of a liquid are closely spaced, and so their motion is still random, but much more limited. The particles slip past and collide with near neighbors. Solids have a definite shape and volume. Particles of solids are in fixed positions and collide only with near neighbors.
What is matter?
When we look at this, we can understand this based on the forces that hold the particles together. You know, for example, what holds a liquid together? A lot of people think what holds a liquid together is gravity, but is gravity really holding the liquid down? You know? And it turns out no, because a liquid molecule is lighter than dust, much lighter than a piece of dust. And so, if you were to blow on the surface, it wouldn't create an aerosol of dust. You know, it wouldn't create an aerosol of molecules because the particles are stuck together like a glue. And so there's something sticky on the surface of these particles, and it's causing them to stick together. Whereas these particles don't stick together so well, and so what happens is they can vaporize. Now, if we were to wash off the glue, then these particles would just vaporize and the gas would stay. But this glue is part of the molecule themselves, so you can't wash it off. Here, these are very sticky, so they don't break apart. Here, they aren't quite as sticky. In other words, what's holding these particles together are the bonds, either covalent bonds, ionic bonds, or metallic bonds here. Over here, when we look at the particles here, there are forces holding these together. These are electrical forces in nature, and we call them intermolecular attractions or intermolecular forces. Okay, here, there's nothing really holding them together, so they're free to disperse.
So, Professor, well, when you have plaque on the brain like Alzheimer's, would that be gas, liquid, or solid?
I would assume it is a solid.
Solid.
Plaques, plaques and angles, solid. Those have different forces with those together. Okay, so this is a liquid here. This is water. This is really slowed down. This is super slow motion because if you look at the timer here, this is in picoseconds. 0.2 picoseconds. It's taking a long time to get to 0.3 picoseconds. So this is really slow motion. But what this shows is that this shows these blue things are these attractions that form and disappear. Form and disappear. In other words, these are attractions between the hydrogens and the oxygens. The hydrogens in water are positively charged. They have a positive charge associated with the polarization of electron. The oxygen is negatively charged, so we have a positive-negative attraction like this. But it's weak, so these aren't real bonds. These are covalent bonds here, you can see. I'm showing you the springs here. So this is the glue that holds these together. The glue is the electrical attractions between the hydrogens and the oxygens. It's not gravity, but it's this glue. So it depends on how strong the glue is, it's going to lead to certain physical properties, like water. Water flows. If the glue is very strong, there's more resistance to flowing. So for example, maple syrup doesn't flow so easily. That means the glue, these molecules must be glued together more strongly. Versus ethanol or some alcohol. Alcohols flow more easily than water. Therefore, what's holding the molecules together is weaker. That's called viscosity. So we're going to look at a number of physical properties of liquids that depend on how strongly these are held together. These molecules are held together. Let's take a look at some of those. These are the learning objectives. Did I talk about Dalton's law yet? No? I guess I did not talk about that. Well, let me talk about it here. Well, we needed Dalton's law for the previous chapter, chapter 14. Answer that one problem, number 39. This is chapter 15. Number 39, that one actually belonged in the advanced section. That should have been in the standard section. Because I think some Chem 1A students would even have trouble with that one. Number 39 was not an easy question. We did Avogadro's in chapter 14. Now we're going to do Dalton's in chapter 15. So what Dalton's law says is that P total is equal to the sum of what we call the partial pressures. So the pressure of gas 1 plus the pressure of gas 2 plus however many gases are in the mixture. That would be it. And so an easy one would be air. Let's say I had 1 atmosphere of air. 1 atmosphere of air consists of 0.8 atmospheres of nitrogen plus 0.2 atmospheres of oxygen. This would be Dalton's law. But with Dalton's law, we have to make sure that volume here. So it says Dalton's law of partial pressure. Total pressure exerted by a mixture of gases is the sum of the partial pressure of the gases in the mixture. The partial pressure of any individual gas in the mixture is the pressure that the gas would exert alone if it occupied the same volume at the same temperature. And so in other words, we keep the volume the same mathematically. And so if I had 1 liter of air, that would be 1 liter N2 and 1 liter O2. So the volume's all the same. They're all in the same formula. Versus Avogadro's law. Avogadro's law looks very similar, except what we say is V total. V total is the sum of the volume fractions, partial volumes. Volume 1, volume 2, plus however many gases we have there. And so if I have air, 1 liter, then I would have 0.8 liters of N2 and 0.2 liters of O2. However, the pressure's got to be the same. So all the pressures are 1 atmosphere. If we go back, we can see that that was the case here. This is chapter 14. Although, you know, it's kind of tricky. Avogadro's law, volume of gas at constant temperature, well, temperature is always going to be fixed, otherwise we start messing. But this is very important. And pressure. And so the pressure's got to be fixed here if we're dealing with Avogadro's law of combining volume. So pressure's fixed here. Pressure is fixed. Law of combining volumes. Then we go to chapter 15. Dalton's law. Volume is fixed here. Same volume means the volume is constant. Same volume. A scientist sets up an artificial atmosphere with 4 gases. Okay, so they're setting up an artificial atmosphere with 4 gases. They're going to have 0.78 bar of nitrogen and 0.21 bar of oxygen, 0.009 bar of argon, and 0.025 bar of water vapor. H2O gas. What is the total pressure? So what they're going to do is they're going to stuff all these into the same container. If they stuff them all into the same container, then the volume of nitrogen is equal to the volume of oxygen, which is equal to the volume of argon, which is equal to the volume of water vapor. So all the gases occupy the same volume. So the volume's fixed. And so what is the total pressure? Well, let's see. The total pressure, this would be Dalton's law. And so the total pressure would be the sum of the partial pressures. So if I have 0.78 bar plus 0.21 bar gives me 0.99 bar. So we just take the sum, we get P total, which is going to equal, let's figure out what equals to. This would equal 5 and 9 is 14. 1.034 bar. Is that what you guys get? Let's see if I did the additions correctly. So we just add up all the partial pressures. I must not have done it correctly. I'm going to use the calculator. Let me use the calculator for this rather than do it in my head. And so 0.78 plus 0.21 plus 0.009 plus 0.025. 1.024 bar, sorry. 0.24. allowed 2 decimal places. So this rounds to 1.02 bar. I don't like this diagram here. In order for Dalton's law to work, what has to be constant? In order for Dalton's law to work, what has to be constant? The volume. And so that means volume of nitrogen should be the same as the volume of oxygen, which should be the same as the volume of the mixture. But when I look at this diagram, it's obvious to me that the volumes aren't the same. This is a 1 liter flask plus this little elbow here. This is a 1 liter flask, but look at the volume in the elbow. It's different, right? And this is a 1 liter flask plus this volume in the elbow, which is clearly different. And so I don't like this figure because if both the volume and the pressure change, then it's a composite. It's easiest not to mess with that, both variables. We can figure it out, We figure it out by doing both a volume and a pressure change. But we're going to pretend this. We're going to pretend we didn't use this instrument. Do you know what this instrument's called here? Do you recognize that? Probably not, because that was way back. How long ago was that? That was way back at the beginning of the semester. Chapter 4. Let's take a look. I forgot what that instrument was called way back in chapter 4. This instrument is called a manometer. And so what you want to do is you just want to do a little bit of review, to go along. Otherwise, you got to start reviewing. I used to like reviewing for the final, starting in the first week, and I never stopped. I'd always review from the beginning of class every week, from week 1, because it's easy to forget. I mean, chapter 4 was so long. So this is a manometer. So what we're going to do is we're going to pretend the manometer is not there. If the manometer is not there, we're just using, we don't have to use manometer. There's lots of mechanical pressure gauges, electrical pressure gauges, so we'll just stop here. And so what do we have? We have 1 liter of nitrogen plus 1 liter of oxygen yields how much mixture? 1 liter mixture. What has to change? The pressure has to change. It's Dalton's law. And so if I have 186 millimeters of nitrogen plus 93 millimeters of mercury, 93 millimeters of mercury of oxygen, what's the total? The total is going to be 186 plus 93, which gives me 279. So I'm just going to cram both gases in the same 1 liter. Pressure is going to go up. This is Dalton's law of mixture. One of the key applications of Dalton's, in general, in stoichiometry, we like to use Avogadro's because stoichiometry, Avogadro's is much easier. You can do the calculations a lot quicker with Avogadro's. But sometimes we're forced to use Dalton's. One of the applications where Dalton's works out very nicely is when we have a mixture of water vapor and a gas. And so this is an oxygen generator. We use KClO3, a solid salt here, which decomposes with heat. There's a little bit of MnO2 as a catalyst to speed it up. And so if we heat KClO3 in the presence of MnO2, we can generate oxygen quite easily. We generate oxygen, and this oxygen usually is collected underwater like this. And so we can figure out how much oxygen we collect. So it's bubbled through water. But if you bubble a gas through water, what you're going to do is you're going to saturate it with humidity. Saturate the water vapor. It's like an indoor swimming pool. You go to an indoor swimming pool, the air around the swimming pool is saturated with water vapor, so it's at 100% humidity. So what we're going to assume is that the oxygen that's trapped in here is at 100% relative humidity. Therefore, this is not pure oxygen gas. This is a mixture. This is a mixture of oxygen and water vapor. So how much oxygen do we have? How much water vapor do we have? Okay, so we have a choice. We can visualize this mixture of oxygen and water vapor as a Dalton's mixture or an Avogadro's mixture. If we visualize this mixture of oxygen, which is the gas, and water vapor, as Avogadro's, then a certain fraction of this volume would be oxygen, probably a large fraction, and a certain fraction of this volume would be water vapor. However, the easiest, let me tell you, is to visualize this as a Dalton's mixture. When we collect gases over water, it's best to visualize this as a Dalton's mixture, meaning that what is the volume of pure oxygen? The volume of pure oxygen is the volume of the container here, up to here. What is the volume of water vapor? The volume of water vapor is the exact same. And so how many milliliters of oxygen did we collect? This many. How many milliliters of water vapor did we collect? The exact same amount. That many. And so what's the difference? The difference is the pressure. And so we did this in lab. We did a trick. Water levels inside and outside the test tube are equalized. In other words, we have the water level inside the test tube and the water level outside the test tube. It acts like a seesaw. So inside the test tube, we have this water level. Outside the test tube, we have this water level. Now, if the two levels are equal, then the weights inside and the weight outside are the same. If the levels are unequal, let's say inside the test tube is like this, that means that inside the test tube weighs more than outside. Or if outside's like this, then the outside weighs more. And so what we need to do is we need to raise and lower the test tube until both levels are equal. When both levels are equal, that means the water pressure inside is equal to the water pressure outside. Actually, I'm actually over time. Since we stopped taking the break, I'll cut it here.